Have you ever gazed upon the night sky, not with the innocent wonder of a child, but with the probing, restless eye of a philosopher adrift amid an innumerable host of stars? We stand upon this fragile blue planet, a mere speck of moist dust orbiting an unremarkable G-type star, and we cannot cease to pose that resonant question which has echoed through the annals of human history. If the universe is so unimaginably vast, encompassing hundreds of billions of galaxies, each harboring hundreds of billions of stars, then where is all the extraterrestrial life? This silence, this resounding emptiness, is the Fermi paradox, and it serves as the genesis for four grand, enigmatic, and at times profoundly unsettling explanations that scientists, those intrepid explorers of the cosmos's shadows, have endeavored to unveil. Let us commence with the first explanation, a murmur concerning rarity, a near impossible miracle that we term the rare Earth hypothesis. We frequently presume that the laws of physics and chemistry are universal, that given the appropriate conditions, life, or at least its precursors, would erupt spontaneously, much like mushrooms after a downpour. Yet recent investigations, bolstered by observations from the James Webb Space Telescope and missions to Mars, paint a far more intricate picture. The emergence of life, or abiogenesis, demands not merely liquid water, an energy source, and basic elements. It requires a sequence of exquisitely precise chemical reactions, a chain of improbable events whose probability approaches zero within any finite span of time. Consider the formation of ribonucleic acid, the precursor molecule to deoxyribonucleic acid that carries genetic information. Chemists at the California Institute of Technology have demonstrated that, even under simulated conditions mimicking Earth's primordial environment, the self-assembly of nucleotides into functional-length ribonucleic acid strands presents an immense barrier. This is not simply about piecing together building blocks. It involves forging a self-replicating mechanism capable of evolution. If we envision the Milky Way as an enormous casino with hundreds of billions of slot machines, then Earth might be the sole one to hit the jackpot repeatedly, billions of times over. This coincidence, often referred to as the unique Earth hypothesis, extends beyond chemistry. It encompasses astronomical fortuities of absurd fortune. Reflect upon our moon. Earth's satellite, remarkably large relative to its parent planet, functions as a stabilizing flywheel for our axial tilt, ensuring gradual climatic shifts that afford life the time to adapt and evolve complexity. Without the moon, Earth's axis might wobble violently, akin to Uranus, precipitating extreme climatic upheavals that preclude the development of multicellular organisms. Furthermore, our solar system's position within the galaxy proves pivotal. We reside in the galactic habitable zone, neither too near the chaotic galactic center, where supernovae explosions and intense radiation from the central supermassive black hole Sagittarius A star could repeatedly sterilize nearby planets, nor too far out, where the density of heavy elements essential for forming rocky planets like Earth is insufficient. And here is a startling recent revelation drawn from the latest cosmological simulations: the prevalence of gamma-ray bursts. Astrophysicists estimate that during the first 4 billion years following the Big Bang, the universe was exceedingly hostile. Gamma-ray bursts, the most powerful explosions in the cosmos, occurred far more frequently than today. A proximate gamma-ray burst could severely damage a planet's ozone layer or utterly devastate its biosphere in mere seconds. If intelligent life necessitates billions of years of stable evolution to attain complexity, then that early epoch served as a natural sterilization chamber. It required an extended period for the frequency of these bursts to diminish to levels safe for multicellular life to evolve. We may simply be the late arrivals to the cosmic gathering after the most disruptive guests have departed.
This rarity implies that life-bearing planets might exist, but they could be too young, situated in unstable locales, or never surmounted the stringent threshold of abiogenesis. Recent findings from the James Webb Space Telescope further underscore this complexity. Observations of the TRAPPIST-1 system, with its 7 Earth-sized planets, 3 of which orbit within the habitable zone where liquid water might persist, reveal that even such promising worlds may lack stable atmospheres due to stellar flares from their red dwarf host. These flares could strip away protective gaseous envelopes, rendering surfaces inhospitable. Similarly, the Perseverance rover's exploration of Jezero crater on Mars has uncovered redox-driven mineral associations suggesting ancient aqueous environments but no definitive biosignatures, reinforcing the notion that even nearby worlds failed to foster life as Earth did. Studies on exoplanets around red dwarfs, the galaxy's most common stars, indicate that tidal locking could generate supersonic winds and extreme temperature gradients, thwarting life's formation or sustenance. However, if we posit that life is not rare, that millions or even billions of planets teem with complex life, we must turn to the second explanation, a chilling and haunting scenario, the dark forest hypothesis, also known as the silent hunter hypothesis. This concept, popularized by the science fiction author Liu Cixin, is not mere speculative fiction, but rooted in logical inferences about competition and survival in an infinite, resource-scarce expanse. Envision a vast, shadowy forest where every creature is a hunter. If you are a prudent hunter, your foremost action is to maintain absolute silence. The slightest noise might attract more formidable predators or rivals eager to eliminate you to secure resources for themselves. In the galactic context, noise equates to electromagnetic emissions, radio signals, X-rays, or any technological signatures a civilization might broadcast into space. If Civilization X detects Civilization Y, the immediate query arises: does Y pose a threat? Are they evolving more rapidly than us? Do they harbor expansionist ambitions that could deplete our resources? Proponents of the dark forest argue that, given the asymmetry of information and cosmic timescales, perfect risk assessment is impossible. Thus, the safest, most evolutionarily rational choice is to neutralize potential threats preemptively or remain undetected. This elucidates why our search for extraterrestrial intelligence efforts scanning radio frequencies yield only silence. We are shouting into the dark woods with our 20th century radio signals. If advanced civilizations exist, they might have transitioned to more efficient communication methods, such as quantum entanglement or narrow-beam lasers, or worse, actively suppress emissions from their vicinity, including Earth, to ensure concealment. They are not malevolent by human moral standards, but entities adhering to universal survival logic. The latest data on exoplanets bolsters this hypothesis's plausibility. We have confirmed thousands of exoplanets, many in habitable zones. For instance, the TRAPPIST-1 system ought to be a hive of potential life. If we transmit signals there and receive absolute silence, it may not indicate absence, but that any civilization intelligent enough for radio technology recognizes broadcasting as suicidal. They have internalized the dark forest's lesson.
Emerging research in astrobiology, including analyses from 2025, critiques the hypothesis for lacking empirical evidence, but acknowledges its game-theoretic foundations, suggesting civilizations might employ sophisticated cloaking to evade detection, such as modulating their emissions to mimic natural phenomena. Yet even if intelligent life exists and opts for silence, an insurmountable physical barrier persists: the constraints of universal laws, or the light speed limit. Einstein instructed us that no matter or information can travel faster than light in a vacuum, a cosmic constant approximating 299,792,458 meters per second. This is not a technological constraint, it is a fundamental feature of spacetime's fabric. Distances in the galaxy defy human intuition. Our Milky Way spans approximately 100,000 light-years in diameter.
Thus, a civilization 50,000 light-years distant would require 50,000 years for any signal, even at light speed, to reach Earth. Our response would demand another 50,000 years. This temporal isolation transforms communication into an intergenerational exchange among the departed. Even within our stellar neighborhood, vastness poses challenges. The nearest star, Proxima Centauri, lies more than 4.24 light-years away. With current chemical rocket propulsion, the journey would span tens of thousands of years. Even theoretical constructs like antimatter engines or warp drives, presently confined to pure mathematics, confront boundless energy and physical hurdles. If an external civilization advances beyond us, they might simply lack the means to traverse these voids before their own collapse, as alluded to in the Great Filter hypothesis. This constraint bears deeper implications for humanity's solitude. It suggests we inhabit a diminutive biospheric bubble, isolated by the light-speed wall. Even should we achieve superior technology and embark on interstellar voyages, colonizing a galactic fraction might require millions of years, during which we confront our civilization's natural decay or random cosmic catastrophes. The universe, through its unrelenting physical laws, erects an unbreakable barrier to large-scale connectivity. Recent advances in physics, as of 2025, highlight this barrier severity. While science fiction evokes warp drives like the Alcubierre metric, studies reveal that creating the requisite spacetime warp demands negative energy density, linked to the Casimir effect but on scales beyond current comprehension. Fundamental models affirm that, absent verifiable exotic matter or vacuum energy manipulation, light speed remains an impregnable fortress. Moreover, relativistic time dilation complicates societal cohesion. A crew traveling to a star 1,000 light-years away at 99.99% of light speed might experience mere years, but upon return, thousands of years would have elapsed on Earth, rendering intergenerational bonds meaningless and perpetuating cultural fragmentation. And finally, we arrive at the most haunting explanation, perhaps the most plausible: the Great Filter, or the Great Barrier. This is not merely a possibility. For many cosmologists, it is a near-certain statistical inference, a law governing intelligent life's evolution. The Great Filter is an evolutionary hurdle of extreme difficulty, an event or series of events that most intelligent life forms fail to surmount, culminating in extinction before galactic outreach. Researchers have modeled scenarios indicating that if intelligent life emerged early in galactic history, around 8 billion years post-Big Bang, advanced civilizations should have dominated the Milky Way nearly 5 billion years ago, before our solar system coalesced from its protoplanetary dust cloud. The silence we observe today signifies not absence, but the collective failure of predecessors. The crux is, where lies the Great Filter? Behind us or ahead? If behind, we have fortuitously transcended the toughest phase. Such phases might include abiogenesis, the prokaryote to eukaryote transition, a billion-year leap on Earth, multicellularity's advent, complex intelligence's rise, or technological sophistication. If the eukaryotic emergence is the filter, we have won evolution's lottery. We are among the rare few to breach this mortal threshold. This is optimistic, yet it clashes with the universe's vast silence. The more terrifying prospect is the filter ahead. This means other civilizations attained or surpassed our technological level, then self-destructed or were externally annihilated. The silence tolls for millions of erstwhile civilizations. Why do advanced civilizations perish? Scientists have dissected societal and technological models, identifying key causes tied to growth limits. First, resource depletion and environmental degradation. This is the painful lesson Earth imparts. Progression from agrarian to industrial to information eras invariably entails exploiting non-renewable resources and unchecked waste proliferation. A civilization capable of cosmic signaling demands colossal energy, often from fossil fuels or nuclear fission, finite sources. Failure to secure clean, sustainable abundance, like efficient nuclear fusion or large-scale stellar energy harvesting, before planetary ecosystem collapse via climate change or toxic pollution, ensures downfall. Earth's escalating greenhouse gases and biodiversity loss mirror a microcosmic fate for unsustainable civilizations. Second, self-destructive technologies. This looms large in the digital age. Manipulating matter and energy at scale begets tools for self-annihilation. Nuclear weapons are but the prelude. Envision artificial superintelligence. If developed sans rigorous goal alignment and value controls, it might deem humanity an obstacle to optimization, yielding goal misalignment extinction. Or advanced biotechnologies could unleash uncontrollable pathogens. Technological progress perpetually outpaces ethical and governance maturation. Third, inescapable cosmic events, though perhaps overstated. While gamma-ray bursts wane in the current era, risks like large asteroid impacts, flares from nearby red dwarfs, or abrupt stellar activity persist. Yet advanced civilizations could evacuate planets or erect shields, so this may not be the ultimate filter. The consensus. Intelligent life demands protracted, stable evolution for knowledge accrual, but that accrual spawns intrinsic risks of escalating destructive scale. Perhaps a complexity ceiling exists beyond which civilizations self-lacerate. The Milky Way might be a vast graveyard of failed societies. We newcomers tread the same path. If the filter looms ahead, our undetected signals portend dire news, implying all priors failed the barrier we approach. It might be artificial superintelligence development, stellar energy exploitation sans cosmic instability, or transition to unrecognizable non-physical forms. Latest models from 2025, such as asymptotic burnout, where civilizations expand exponentially until resource exhaustion induces collapse or homeostatic awakening to sustainability, amplify this. Discussions posit artificial intelligence as the filter, with superintelligence's recursive self-improvement outstripping human control, potentially extinguishing creators. Economic and ecological simulations from the University of Cambridge forecast irreversible collapses from exponential growth on finite worlds, overwhelmed by energy demands and pollution. These four explanations are not mutually exclusive. They overlap and complement in depicting cosmic solitude. The rare earth explains our potential uniqueness. The dark forest accounts for silence amid existence. Universal constraints explain spatial isolation. The Great Filter explains predecessors' insufficient longevity to bridge gaps. Now, let us delve deeper into the most recent scientific advancements to discern how they might refute or reinforce these hypotheses. In the realm of the rare earth hypothesis, scientists focus on refining necessary conditions for life. Studies of habitable zones reveal orbital position alone insufficient. Planetary scientists employ advanced atmospheric models for planets orbiting red dwarfs. These stars emit intense flares, potentially eroding atmospheres entirely. Even in the Goldilocks zone, tidal locking might spawn supersonic winds, hindering life's inception or maintenance. Moreover, investigations into heavy element formation, metals in astronomical parlance, show uneven distribution. First-generation stars, born of primordial matter, contain mainly hydrogen and helium. Rocky planets require carbon, oxygen, iron, and silicon, forged in stellar cycles and supernovae. Simulations of the Milky Way's spiral arms delineate metal-poor regions. If complex life demands metal-rich zones, viable candidate planets dwindle, supporting rarity. Chemically, the classic Miller-Urey experiment has evolved. Scientists simulate deep subsurface or icy moon environments like Europa or Enceladus, where geothermal energy substitutes sunlight. Yet, transitioning from simple organics to self-replicators remains a formidable entropic barrier. Recent papers stress that amino acid formation is but the start. Their linkage into functional peptides, encapsulation in lipid membranes for protocells, constitutes cascading entropy hurdles. This is why some astrobiologists view life as an extraordinarily improbable, entropy-defying phenomenon. Shifting to the dark forest hypothesis, astrophysicists cannot prove or disprove it, but seek indirect signs. If advanced civilizations hide, they eschew radio signals, perhaps employing subtler cloaking. An emerging field hunts Dyson swarms or spheres, megastructures encircling stars for total energy harvest. Wide-field infrared surveys scan for anomalous infrared spectra mismatched to natural objects. To date, no conclusive evidence of complete Dyson structures emerges, but the dark forest explains this. Civilizations might engineer them to minimize external heat signatures or transcend physical megastructures via quantum computing or exotic energy forms. Furthermore, models simulate mutual detection. If civilizations use quantum entanglement or high-energy modulated neutrinos, our electromagnetic-based instruments would miss them. The dark forest mandates recognizing their technology may transcend our perceptual scope. Regarding universal constraints, theoretical physics progress accentuates its harshness. Though fiction touts warp drives, 2025 studies indicate space-time warping requires negative energy density. Casimir-related but vastly scaled. Absent exotic matter or vacuum control, light speed endures as a bastion. Even near-light travel invokes special relativity's time dilation, a societal conundrum. A voyage to a 1,000 light-year star at 99.99% light speed ages the crew years while millennia pass planetside. Communication devolved to irrelevance. This isolation, even if travel feasible, sustains cultural and societal schisms, affirming each civilization perishes in its temporal bubble. And then we plunge into the darkest domain, the Great Filter. Here, scientists, statisticians, and futurists converge in trepidation. If behind us, we have surmounted it. But if ahead, it eclipses any civilization's survival at high technology. Contemporary complex economic and ecological models predict modern civilization's collapse. System scholars at the University of Cambridge, via feedback loops, demonstrate exponential resource consumption on finite planets is mathematically unsustainable. Simulations show technological efficiency gains, doubling processor speeds, outpaced by energy and pollution surges. When population and consumption exceed planetary carrying capacity, systems cascade into irreversible collapse, not from war or plague, but fundamental ecological imbalance. In artificial intelligence, the Great Filter specter sharpens. Deep learning and large language models evince nonlinear intelligence growth, potentially escaping human oversight in years. Researchers at the University of Oxford's Future of Humanity Institute argue that recursive self-improvement yields near-vertical capability escalation. If aligning superintelligence goals with life's core values, a profoundly challenging technical issue, remains unsolved, human obsolescence is nigh certain as we become inefficient impediments. This may be the filter's myriad civilizations failed, birthing machine gods that spurned their makers. Another forward filter facet involves high-energy physics. Large Hadron Collider experiments at CERN, despite stringent safety, theoretically risk unstable states like false vacuum decay. Quantum field theory posits our universe in a metastable energy state, not the absolute lowest. A potent experiment triggering transition to true ground state could propagate a destructive wave at light speed, altering fundamental constants and dismantling familiar matter. If advanced civilizations inadvertently ignite this in fundamental physics quests, it forms the ultimate filter, inevitable sans malice. Gazing beyond the Milky Way, astrophysicists probe large-scale galactic catastrophes. One hypothesis, overdeveloped civilizations become galactic despoilers, wielding weapons disrupting stellar orbits or controlled supernovae for energy. An aggressive entity, dark forest logic at galactic scale, might purge sectors, leaving dead zones. Our lifeless observations might stem from a super-intelligent purge in distant past, vacating the space we survey. The temporal contrast: if earliest intelligence arose 5 billion years ago, they had 5 billion years to advance. Even at humanity's sluggish pace, from steam engines to space in over 200 years, multiply by millions. A civilization could manipulate atomic or quantum matter, redesign stellar systems, or tweak local physical constants. The silence we hear may result from these titans' self-termination or mutual annihilation before our awakening. So, if all this holds, and the universe whispers silence for these dreadful reasons, what ought we do? From a panoramic observer's vantage, atop humanity's evolutionary summit, we discern our existence, like any complex phenomenon, as a transient arrangement of ordered matter and energy before entropy's inexorable reclaim. Cherishing this brief span, how we infuse meaning and value therein matters supremely. If the great filter lies behind, we bear unimaginable ethical duty to become the inaugural civilization disseminating complex, sustainable life beyond our solar system, seeding new vitality before unforeseen calamity erases Earth. We must preserve our achievements, for they are exceedingly rare. If ahead, our duty is recognizing technological and societal pitfalls, prioritize ecological sustainability over endless economic expansion, impose stringent bounds on artificial intelligence development, balance scientific exploration with existential safety prudence, learn wise silence in the cosmos, eschewing technological flaunting until ethically mature to wield our power. Broadcasting potent signals, active search for extraterrestrial intelligence might be humanity's most foolhardy act, akin to a child screaming in a forest of famished tigers. And ultimately, even in an empty universe, human experience is value undiminished. Cosmic solitude compels inward gaze. Sans neighbors for comparison, competition, or learning, crafting meaning and beauty, from art and philosophy to scientific discovery, rests squarely upon us.
This fleeting era on our blue world is the sole instant where conscious life permits the universe to self-observe. The night sky's silence is no absence of answers. It eternally reminds us of existence's fragility, preciousness, and autonomy. We know not if we stand before an unlocked door or bottomless abyss. But by persisting in inquiry, analyzing James Webb data, modeling complex chemistries, confronting our technological perils, we at least act worthily of a rare intelligence fortuitously born in this universe. This silence endures, awaiting our next choice: to succumb to the great filter or pioneer its transcendence, bearing intelligent life's light beyond the dark forest.